Hello, this is Richard Hammack's Calculus 1 course. We are in part 5 of the course on integration. Today, lecture 43, the fundamental theorem of calculus. This is the pinnacle of our course. Today we'll take the main concepts from part 1 through part 5 of the course, everything we've covered up until now, and put them together into the fundamental theorem of calculus. It's an important result with staggering consequences. Let me start by reminding you where we've been and also saying a quick word about where we're going in this section. As for where we've been dealing lately with the problem of finding the area A under the graph of a curve y equals f of x and between two x values of A and B. And our approach to this problem was this. We took the interval from A to B and we divided it up into n equal subintervals, each of width delta x, which you'll remember is b minus a divided by n. And then in each subinterval, we took a sample point. So in the kth subinterval, we had a sample point x sub k. And in this picture, I'm drawing it so the sample points are always as far to the right as they can go. Like x1, our first sample point in the first interval, is all the way to the right of that interval. X sub 2, the sample point in the second interval, is always to the right, and so on. And the area A we expressed as the limit as n goes to infinity, where n is the number of rectangles, of the sum of the areas of those individual rectangles, where the area of rectangle k would be its height times its base, f of x of k times delta x. So A is the limit as n goes to infinity, sum from k equals 1 to n, f of x of k times delta x. And we even worked out one of these limits in all of its detail and got the area under the curve. But the way we're going to take this, or the way we did take it, was to actually make a definition from what's going on here. We defined the definite integral from a to b f of x dx to be equal to precisely this limit that gave us area in this situation. Now, it's important to realize that in this definition of the definite integral from a to b f of x dx, this limit doesn't necessarily give you area, because it could be that if your function f of x was ever negative, then some of these heights f of xk would be negative. So you'd get some negative contributions in this sum as well as maybe some positive contributions. And in the end, that doesn't necessarily equal area. It only equals area if the graph of y equals f of x is always above the x-axis. But nevertheless, we defined the definite integral from a to b f of x dx to be this number. It's the value of this limit. So the definite integral is a number that equals this limit. Now, a couple of remarks about the definite integral. I want to point out that in these pictures, we take the independent variable to be x, although we never really mentioned it. We think of it as being an x value. But the value of the definite integral has nothing to do with that variable, x. It's actually just a number. It has nothing to do with a variable. So it doesn't really matter what variable we use in the definite integral. The integral from a to b f of x dx is exactly the same as the integral from a to b of f of t dt. It doesn't matter whether this variable is an x or a t or a y or a z. The definite integral is going to be the same. So we tend to say that x and t are so-called dummy variables. They're there because they're part of the notation, but it doesn't matter what variable we use. The definite integral is always the same number. Okay, with that out of the way, I'm going to kind of jump ahead and tell you exactly what the fundamental theorem of calculus is going to be, and then we're going to kind of work through it. Today's goal is to get to the fundamental theorem of calculus, and it is a link between definite integrals and antiderivatives. And there's several formulations of it, but I'll tell you the most useful one. It's this. It gives you a way of finding the definite integral without evaluating a limit. It states that if big f of x is any antiderivative of little f of x, then the definite integral from a to b f of x dx is simply big F of b minus big F of a. In other words, to find the definite integral, rather than evaluating this limit, you find an antiderivative big F of little f, you plug in b, and you subtract off what you get when you plug in a. Now, you may wonder why that's true, and we're actually going to get to it. So, towards the end of today's lecture, we're going to derive this formula and then work out some examples involving it. But I just wanted to give you a heads up of where we're going. And with that, let's continue developing this idea. So everything I do now is going to be leading up to explaining why this equation is true. I want to start with a motivational example. I want you to consider the area under the graph of f of x equals x plus 2 between 0 and some value of x, between 0 and x. And here's the picture. The graph of f of x equals x plus 2 is a straight line, its slope is 1, and its y-intercept is 2. So it looks like this. And on the x-axis, we're looking at the interval between 0 and some value of x. And that value of x is unspecified. It could be anything like 1/2, 1, 2, pi. Think of that as just a variable of x that could have any value. And we're looking at the area under f of x equals x plus 2 between 0 and that x. Now, if you think about that, that x could have different values. And as you increase x, the area increases as well. So this area under the curve would actually be a function a of x. For any x value, a of x is the area in square units of this shaded region. So as x gets big, a of x is getting bigger and bigger. If you decided to make x smaller again, then a of x would start getting smaller. A of x is just a function of x. Now, what I want to do here is see if we can get an actual formula for this a of x, and then we're going to see an interesting pattern pop out. A of x, this shaded region, really consists of two familiar pieces. There's a rectangle at the bottom and a triangle at the top. And as x changes, those shapes, the rectangle and the triangle, they get bigger as x gets bigger. And let's think about their areas. The rectangle always has a height of 2, but its base is x. So this rectangle is x by 2 units. So its area is 2 times x, square units. Whereas if you look at the triangle, its base is x, and also its height is x, because this line has slope 1. So rise over run has to be equal to 1. So if the base is x, then the height is x. And we can get a formula for a of x here. It's the area of the triangle plus the area of the rectangle. And the area of the triangle is 1/2 base times height, that's 1/2 x times x, plus then the area of the rectangle is height times base, which is 2 times x. So a of x is 1/2 x squared plus 2x. So as x changes, the area a of x changes as well. For any x, it's always 1/2 x squared plus 2x square units. Now, I want to point out a really interesting thing that's happening in this example. Think about the function we started with. It was f of x equals x plus 2. I'll tally it down here. The function was f of x equals x plus 2. And then we looked at the area a of x under the graph of that function, and we got it right here. So the area under the function is a of x equals 1/2 x squared plus 2x. Now, you may already see it, but there's a really interesting connection between this function little f of x and this area function a of x. Notice that if you differentiate the a of x equals 1/2 x squared plus 2x, you get x plus 2. If you differentiate the area under the function, you get the function itself. And it turns out that this is not a coincidence. This is always true. And that's part of the fundamental theorem of calculus. And this is just sort of a paraphrasing of it, just to give you an indication of how it works. It turns out that the area under the graph of f of x is an antiderivative of f of x in the sense expressed in this picture. In other words, no matter what this function was, not just x plus 2, but any other function, if you make this area function a of x, it's always going to be an antiderivative of your original function f of x. That if you take the derivative of the area function, you get the function that you started with. That's the fundamental theorem of calculus, or part of it. Now, to make this a little more precise, I want to continue with this motivational example, and we're going to extract out of it an exact statement for the fundamental theorem of calculus. So here's our motivational example, and I've changed things just a little bit, just so we don't have notation that's colliding. I'm using the independent variable here to be t. So this is the t-axis, and x is just a value of t. So a of x in this picture, you'll remember, is the area under the graph of y equals f of t between 0 and x. And what we saw in the previous slide is that d dx of a of x equals f of x. The derivative of area equals the original function. Now, let's analyze what's going on here. We know that a of x is the area under that curve. It's the definite integral from 0 to x of f of t dt. That was one of the interpretations of a definite integral. So this integral from 0 to x, f of t dt, which gives the area a of x, it's actually a function of x. As you change the variable x, this upper limit of integration changes, and so the value of the integral from 0 to x, f of t dt, is going to change as well. It's a sort of an unusual way to define a function, but it actually is a function of x. Different values of x give you different values of this definite integral. In fact, it's always equal to the function a of x for any x. So taking that over to the equation that's going on here, a of x, we said, was equal to the definite integral from 0 to x f of t dt. The previous line says that the derivative of this function integral from 0 to x f of t dt equals f of x. So it's just a different way of writing what we had in the previous line. But I'm writing it this way because the statement that you see here is our first formulation of the fundamental theorem of calculus. This is called, the thing that's going on in this line right here, is called the fundamental theorem of calculus, part 1. There are going to be 2 parts of this, and this is part 1. And it states that what happened in this motivational example is always going to happen, not just for f of t equals t plus 2, but for any f of t. Fundamental theorem of calculus, part 1. If f is continuous on the interval from a to b, then the function a of x, which is the integral from a to x f of t dt, is differentiable on the interval from a to b, and the derivative of the integral from a to x f of t dt equals f of x. So it's saying exactly what we set up here, or what we determined up here, but for any general function f. So the way to look at this fundamental theorem of calculus part 1 is to think about the picture that's going on here that echoes the motivational example that we had. You've got a function y equals f of t that's defined on the interval from a to b. And x is just some value between a and b. It could be any, it's a variable value. It could be any value between a and b. And you think about the function a of x, which is the integral from, should be the integral from a to x f of t dt. That's this shaded area. And that's going to change as x changes. It's a function of x. Integral from a to x f of t dt is a function of x. And the fundamental theorem of calculus just says that the derivative of that function is f of x. Let's take a look at an example of this fundamental theorem of calculus part 1. Let me give you an explicit value for our explicit function for f. Think about f being the function sine of t plus 2. So here's the graph of sine of t plus 2. It's the graph of sine just moved up 2 units. And imagine you have a x value of pi here, or t value of pi, and then x is some maybe later on subsequent value of t further down the line from pi. Think about this shaded area. That area is the integral from pi to x of sine of t plus 2 dt. And that's a function of x. As x increases, that shaded area gets bigger. So the integral from pi to x sine of t plus 2 dt increases. It's a function of x. And what the fundamental theorem of calculus part 1 is saying is that the derivative of that function is going to be your f. It's going to be sine of t plus 2, or sine of x plus 2. The derivative of the integral from pi to x of sine of t plus 2 dt is sine of x plus 2, your f of x. So that's the fundamental theorem of calculus, part 1. Now, admittedly, part 1 is probably not the most useful formulation of the fundamental theorem of calculus. We're going to, in a few moments, look at a consequence of the fundamental theorem of calculus part 1, which we're going to call the fundamental theorem of calculus part 2, and it's going to be the most useful. The part 2 is going to be the most useful one. But for now, we're going to look at this part 1 of the fundamental theorem. Now, real quickly, I want to just sketch the proof of this. it's not going to be a full, I'm not going to dot every I and cross every T here, but just I want to give you an indication of why you should believe that the derivative of the integral from a to x f of t dt is equal to f of x. So in the proof, what we need to do is up here, if a of x is the integral from a to x f of t dt, we need to show that its derivative is f of x. We need to show that a prime of x equals f of x. Now, down here, I'm just reminding you of what that means. The derivative of a prime of x would be, by definition of the derivative, limit as h goes to 0 of a of x plus h minus a of x divided by h. That's the definition of a prime. We need to show that that's equal to f of x. So if we can show that these two things are equal, then we've shown this, and we've proved the fundamental theorem of calculus part 1. So I'm going to draw you a little picture here. Here's our y equals f of t, and under that is the a of x function. And in this limit down here, we don't just have an a of x, which would be this area here. We also have an a of x plus h. So imagine you take this x and you add a little bit of length to it. You go up to x plus h. That's right there. Then this shaded area got a little bit bigger. You added to it some darker shaded area right here between x and x plus h. And look at that darker shaded region. If you think about it, it's a of x plus h minus a of x. A of x plus h would be this entire shaded region, all of this between a and x plus h. And then minus off a of x, that's the light shaded region. So the darker shaded region is a of x plus h minus a of x. And we're going to look at this and we're going to convince ourselves that this limit actually holds true. Continuing with this picture, I want you to let little m be a y value that's the smallest f of t value on the interval from x to x plus h. And in this picture, it would happen to be about right there. So as the function goes from x, as the variable t goes from x to x plus h, the lowest you get is this little m. Whereas let's let big M be the highest you get on the interval from x to x plus h. So for this function, that occurs right here. That's the highest you get for t values between x and x plus h. So that's big M. And look at the rectangles that are formed. We have a short rectangle here whose base is h and whose height is m. And then we have a taller rectangle whose base is h and whose height is big M. And this dark shaded area, which is a of x plus h minus a of x, is inside the tall rectangle, but the smaller rectangle is contained entirely in it. So what we get is the following. This dark shaded region, which is a of x plus h minus a of x, it's less than or equal to h times big M, the base h times the height big M of that tall rectangle. But little h, h times little m, which is the area of the rectangle here, the shorter rectangle, that's inside the area a of x plus h minus a of x. So it's less than or equal to a of x plus h minus a of x. So we get that this dark shaded region, a of x plus h minus a of x, lies between h times little m and h times big M. And the next thing we're going to do is we're going to take that inequality and we'll divide all parts of it, all three parts, by h. So on this side we get m is less than or equal to a of x plus h minus a of x divided by h less than or equal to m. And you can see why we're doing this, because now we're getting down to an expression in this derivative. Okay, so now think about in this limit down here that we're interested in, h is approaching 0, so this dark shaded area is getting skinnier and skinnier, and big M and little m, they're going to be getting closer and closer together. In fact, they're both going to be getting closer and closer to f of x, because x plus h is approaching x, so f of x plus h is approaching f of x, and big M and little m are somewhere between f of x plus h and f of x, so they're getting closer and closer to f of x. So if we take the limit as h approaches 0 of little m, and the limit as h approaches 0 of big M, then the limit as h approaches 0 of a of x plus h minus a of x divided by h lies between those two values. That comes from this previous line that holds for all values of h. So when we take the limits as h approaches 0 of these three quantities, the limits obey this relationship. Now the limit as h approaches 0 of little m is f of x. The limit as h approaches 0 of big M is f of x. And the limit as h approaches 0 of a of x plus h minus a of x divided by h is a prime of x. So there we go. A prime of x is greater than or equal to f of x, but less than or equal to f of x. So the only thing that you can conclude there is that this a prime of x has to be equal to f of x. That's the only way this inequality could hold. And that gives us exactly what we're looking for. It shows that a prime of x equals f of x. And it proves the fundamental theorem of calculus, part 1. So that's why you should believe that this fundamental theorem of calculus is true. Now, we're going to move on to something a little bit more significant. We're going to look at a consequence of the fundamental theorem of calculus, part 1. And it's going to give us a definite integral formula, an actual formula that you can evaluate definite integrals with that totally bypasses the limit process. Now, to derive that formula, I want to start off with the statement of the fundamental theorem of calculus, part 1. d dx of the integral from a to x f of t dt equals f of x. That's just the fundamental theorem of calculus, part 1, restated. Now, if you look at that, it says that the derivative of this function equals f of x. So that would mean that this function, integral from a to x f of t dt, is an antiderivative of f of x, because if you take its derivative, you get f of x. That makes it an antiderivative of f of x. Now, here's what we're going to do. Let's let big F of x be any antiderivative of f of x, of little f of x. Now remember, little f of x has lots and lots of antiderivatives. Big F of x plus c, just take any one of them. Like maybe think about your c being equal to 0, perhaps. So big F of x is any antiderivative of f of x. Well, since any antiderivatives of f of x differ by a constant, and the integral from a to x of f of t dt is an antiderivative of f of x, then it's going to be this antiderivative big F of x plus some constant. So the integral from a to x f of t dt equals the antiderivative big F of x we chose plus a constant. And what we're about to do is we're going to figure out what this constant would be. We're going to figure out the value of c. And one way to do that is in this equation, put in, for this value of x, plug in a. Everywhere you see an x, put in an a. So we get the integral from a to a, f of t dt equals, instead of f of x, f of a plus c. But one of our properties of definite integrals is that when we do the integral from a to a, f of t dt, we get 0. So we have here an equation, 0 equals f of a plus c. Now, that would actually tell you what c is equal to. If 0 equals f of a plus c, then c would have to be equal to negative f of a. Just solve the equation 0 equals f of a plus c. For c, you get c equals f of negative f of a. So we're going to update our formula here. Now that we've found a value for c, we know it's negative f of a. This formula becomes integral from a to x, f of t dt equals big F of x minus f of a. That's just this with the c replaced by f of a. Now, the next thing we're going to do is that this x right here, that also happens right there, we're just going to plug in the number b. Put in x equals b. And you get the integral from a to b, f of t dt equals big F of b minus big F of a. And one tiny little cosmetic thing, remember that this t, we call it a dummy variable. It could be any variable that you choose. Now that we've gotten rid of our x up here, and there's no longer a conflict of notation, let me change that back to an x. So what we get is the integral from a to b, f of x dx, equals big F of b minus big F of a. That's a formula for definite integrals. And it's the one I promised you way back at the beginning of this lecture. It's a formula that gives you the value of a definite integral without a limit. It says all you have to do is find an antiderivative of this little f of x, plug in b, and then subtract off what you get when you plug in a. And that's the value of that definite integral. Now, class, that's really useful. It's so useful, we give it a special name. We're going to call that the fundamental theorem of calculus, part 2. So here it comes. Well, summarizing this, the fundamental theorem of calculus, part 2, is the following. If f is continuous on the interval from a to b, and big F of x is any antiderivative of little f of x, then the integral from a to b, f of x dx, equals big F of b minus big F of a. Let's look at an example of that. Consider the problem of finding the integral from 0 to 2 of x squared dx. And I've drawn the picture over here. Y equals x squared is this parabola, and we're going from 0 to 2, and this x squared is positive. So this definite integral would be the area under the graph of x squared between 0 and 2. Now, you may remember a couple of lectures back, we actually worked out this exact area that's shown here using not the fundamental theorem of calculus, but this limit process. The limit is n goes to infinity of Riemann sums, and we actually came up with the value for that. And do you remember what it was? It's actually 8/3 square units. So we have an idea already, having done this before a different way, what the answer is going to be. It's going to be 8/3. But let's see if applying the fundamental theorem of calculus gives us that same value. So if we want the integral from 0 to 2 x squared dx, the fundamental theorem of calculus says all we need to do is find an antiderivative, big F, of x squared, and then take this difference. So think about finding an antiderivative of f of x equals x squared. Well, that's easy. Big F of x is the integral, the indefinite integral of x squared dx. That's 1/3 x cubed plus c. But the fundamental theorem of calculus says that any antiderivative will work. So since we can use any antiderivative, just make things simple. Take that c to be equal to 0. So big F of x is 1/3 x cubed. So the fundamental theorem of calculus says the value of this integral is going to be this difference, big F of b minus big F of a. In our case, that would be big F of 2 minus big F of 0. Fundamental theorem of calculus says the integral from 0 to x squared dx is big F of 2 minus big F of 0. And let's see, big F of 2 would be 1/3 2 cubed minus the big F of 0. Big F of 0 is 1/3 0 cubed. That's here. And when you combine those, you get 8/3, just as we expected. That's the value of this definite integral. And it's so much easier than working out that limit. And that's why we only use the limit one time to work out an exact value of a definite integral, because you just don't want to do it that way. The limit definition is important because it tells you the interpretations of a definite integral. But when it comes to evaluating definite integrals, you want to use the fundamental theorem of calculus. Now, before we move on, another quick word about this. Big F of x could be any antiderivative. And here, to make things simple, we therefore took c equals 0. But I want to point out that you could actually, if you wanted to, put in any value for c, like, I don't know, c equals 5, if you wanted to. Well, what would happen in f of 2 minus f of 0 here? You'd have a plus c, a plus 5, and then minus that c here, a minus 5. So whatever c you pick, it's going to get canceled out in this difference. So it doesn't even show up in the value here. So for that reason, when you're using the fundamental theorem of calculus and you're working out an indefinite integral to find an antiderivative, just take c equals 0. Make your life easier. A few more examples. Here I've drawn the graph of cosine of x, and look at the graph of cosine of x between negative pi over 2 and positive pi over 2, where the graph crosses the x-axis. Between those two values, cosine of x is positive, and what we want to do in this problem is find the area of that shaded region below the graph of cosine of x and between negative pi over 2 and positive pi over 2. Well, we know from the previous section that that area is going to be the definite integral from minus pi over 2 to pi over 2 cosine x dx. And the thing is that with the fundamental theorem of calculus, we now have a way of computing that. It tells us that we need to, in order to compute this definite integral, find an antiderivative, big F of x, of cosine of x. Well, an antiderivative of cosine of x would be the integral, the indefinite integral cosine dx equals sine of x plus c. But remember, we can make that c equal to 0. So big F of x is just sine of x. So by the fundamental theorem of calculus part 1, the definite integral from negative pi over 2 to pi over 2 cosine x dx is sine of pi over 2 minus sine of minus pi over 2. And sine of pi over 2 is 1 minus, and then sine of minus pi over 2 is minus 1. So 1 minus minus 1 is 2 square units of area. So the exact number of square units of area under this graph between negative pi over 2 and pi over 2 is 2. 2 square units of area. And I always think that's kind of surprising because cosine of x, it seems pretty far off from integer values. You might expect that this area is going to have some multiple of pi in it or something, but no, 2 square units of area in that shaded region, exactly 2. Now, I want to talk a little bit about some notation. This expression, big F of B minus big F of A, it comes up obviously a lot when you're doing the fundamental theorem of calculus. And a lot of times, as you'll see, your antiderivative big F is going to be pretty complicated. And when you do big F of B minus big F of A, you're writing a complicated expression twice there and taking the difference. So there's actually a notation for that, a streamlined notation that the text uses. Big F of B minus big F of A, you write that this way. You write your big F of x, and then you have a bar subscripted by an A and superscripted by a B. And you just read this as big F of x from A to B. And whenever you see that, you will know that that compact little piece of notation simply means F of B minus F of A. Now, some texts, instead of writing that vertical bar, they'll have a little bracket like this, and you read that big F of x from A to B. It's also equal to F of B minus F of A, either one. But our text is going to use this notation. I kind of like the bracket, but I like to see things balanced, so I like to enclose things in brackets. So what I'm going to do in my lectures is write this as follows. Big F of B minus big F of A is big F of x from A to B, written this way, where that bracket is balanced. So in my lectures, I'll write it this way. In the textbook, you'll be reading this, but they mean exactly the same thing. So rephrasing the fundamental theorem of calculus part 2 with this new notation, the integral from A to B, f of x dx, would be big F of x from A to B, where big F of x is just any antiderivative of little f of x. So, for example, think about the definite integral from 2 to 4 of x cubed dx. According to the fundamental theorem of calculus, we just need to find an antiderivative of x cubed and go from 2 to 4. Now, an antiderivative of x cubed, you can do it in your head. That's by the power rule for integration. That's x to the 4th over 4 from 2 to 4. So that would mean you take x to the 4th over 4, you plug in the 4, and then you subtract off what you get when you plug in the 2. So 4 to the 4th divided by 4 minus 2 to the 4th over 4. And if you work that out, that's 64 minus 4. So 60 is the value of this definite integral. For another example, consider the integral from 0 to 1 of 1 over 1 plus x squared dx. So the fundamental theorem of calculus, part 2, says we just need to find an antiderivative, big F, of 1 over 1 plus x squared and go from A to B, from 0 to 1. Now let's think about that. What's an antiderivative of 1 over 1 plus x squared? Remember, tangent inverse of x. We know the derivative of tangent inverse of x is 1 over 1 plus x squared. So it's an antiderivative of 1 over 1 plus x squared. So the value of this definite integral is going to be tangent inverse of x from 0 to 1. That means plug in your 1 to tangent inverse and then subtract off what you get when you plug in your 0 into tangent inverse. Now let's see, tangent inverse of 1, that's pi over 4. Tangent inverse of 0 is 0. So pi over 4 minus 0 is an answer of pi over 4. So this definite integral by the fundamental theorem of calculus is equal to pi over 4. Now remember the limit definition of a definite integral? You really would not want to do one like this using a limit. But with the fundamental theorem of calculus, you get it in just a couple of steps. It's so easy. Let's see. Let's do one more example. How about the integral from 1 to 4 of square root of x plus x dx? And let me convert that radical to a power here because we're going to be thinking about antiderivatives. And it's easier to think about them in terms of powers. So we have the integral from 1 to 4, x to the 1/2 plus x dx. And the fundamental theorem of calculus says, part 2 says we're going to need an antiderivative of this x to the 1/2 plus x, and we'll go from 1 to 4. Okay, antiderivative of x to the 1/2 plus x. Well, that's x to the 1/2 plus x to the power of 1. You could get an antiderivative of both of these terms, these powers of x, with the power rule for integration. So an antiderivative of x to the power of 1/2 would be x to the power of 1/2 plus 1, which is x to the power of 3/2, divided by 3/2. And then an antiderivative of x to the power of 1 would be x to the power of 1 plus 1 divided by 1 plus 1. So that's our antiderivative of x to the 1/2 plus x. And we're going from 1 to 4. So we plug in 4 wherever we see an x, and then subtract off what we get when we plug in 1 for each of the x's. And since we're going to be plugging in numbers, it's convenient to revert back to radicals. So this x to the power of 3/2, let's make that square root of x cubed. And now we plug in a 4 for the x's, here and here, and subtract off what we get when we plug in a 1 for the x's there. And square root of 4 is 2, and that cubed is 8, times 2 is 16. So working through this, we get 16 over 3 plus 8 minus 2/3 plus 1/2. And that turns out to be 73 over 6. So we pretty quickly were able to come up with the value for this definite integral using the fundamental theorem of calculus, part 2. Well, class, we've talked about some big things today. Let me give you a summary. The primary things we came up with were these 2 versions of the fundamental theorem of calculus. Part 1 says that if f is continuous on the interval from a to b, then this function a of x, which is the integral from a to x f of t dt, it has a derivative, and that derivative is d dx of the integral from a to x f of t dt, and it's equal to f of x. Now, that's not the most useful version of the fundamental theorem of calculus. It pops up from time to time. The really crucial one that you're going to be using over and over again is the fundamental theorem of calculus part 2, the consequence of part 1, which is this. It's the one that gives us a simple formula for an for a definite integral. If f is continuous on the interval from a to b and f of x is any antiderivative of f of x, then the integral from a to b, f of x dx, equals big F of b minus big F of a, which we write as big F of x from a to b. Everything we do for the remaining 4 lectures of this course will be concerned with the implications and consequences of this. I'll see you next time. Goodbye.